All right, so we are going to get started again. Oh, thank you. Very efficient over there. Great. So I hope you all enjoyed your lunch, and we'll just try to chew quietly. And we're going to keep moving here. So next we have Jesse Logan with Kotzebue Electric Association talking about solar thermal for an elder housing facility there up in Kotzebue.
Well, I'd like to thank everybody for wearing red today. I brought Valentine's cards for each of you. And this project is not for an elder's facility, excuse me, Brian, but it's for elders' homes. But I'll get into that in a little bit. So I'm Jesse Logan, and I'm with Kotzebue Electric. So Kotzebue is 38 miles north of the Arctic Circle, so intuitively you'd think there wouldn't be a whole lot of solar application up there. But if anybody was in line over there standing in the sun, you notice how much hotter it was standing in the sun versus the shade inside. Well, that's basically the concept that we have been working with there. The key partners, besides KEA, was the Community Energy Task Force that was formed in 2008 to sort of combat the rising, spiking, if you will, cost of fuel in rural Alaska. And over 2008-2009, the Community Energy Task Force raised about $100,000 in donations and labor and weatherized more than 150 elders' homes in town. Also, of course, we've been working heavily with Nally Commission, ASEP, and the NANA Regional. The project goals were to reduce the residential fuel usage for domestic hot water and space heating if applicable, and of course, then to test the efficacy of solar thermal above the Arctic Circle. So as you guys probably know, solar thermal is not a new technology. It's been around for several decades, but to the best of our knowledge, no one has tried to apply it above the Arctic Circle. There are some installations around Alaska, and that's actually picking up quite a bit of steam. Essentially, the way solar thermal works is a supplemental way to heat hot water and or glycol. If any HVAC people are in the room, you're going to understand this pretty easily. And about 20% of the fuel usage in the Northwest Arctic borough is used to heat hot water, so we thought that would be a good place to start. Of course, solar thermal units can be designed in a variety of different ways with a variety of different collectors and different applications for hot water with indirect fired water heaters, direct fire water heaters, tanks, etc. And we'll talk a little bit about that, and if anybody has technical questions, I'm free all day. We'll start with the two main types of solar collectors. This is an evacuated tube collector here. That's David Lindeen and I finishing up the touches on Cassie Driggs' house there. I think that was on the winter solstice this year. I'd like to say, too, that I inherited this project about 18 months ago when I started working for KEA. I'd like to thank Catherine Keith for writing such a grant that allowed me to get on a roof above the Arctic Circle on the winter solstice. Thanks, Kath. Also note the angle of this collector. This is on a pitched roof, and typically we angle a collector for solar about the same as the latitudes, and in Kotzebue about 62 degrees. That's what this particular collector is angled at. We also have a few that are angled at the pitch of the roof at about 22 to 25 degrees. And we're going to try and see which one of those angles collects more annually. As the sun gets pretty high during the summertime, we think that there's a possibility of a higher gain there during certain months. The other type of collector is a flat panel, which you see here, which is basically glass. It's got copper tubing running through there, and the glycol mixture runs through, collects directly from the sun, and then is pumped into the house. So here's a real simple design to get an idea of what solar thermal looks like. You have a collector, whether it's a flat panel or an evacuated tube, and that runs through a glycol mixture depending on your temperature needs. We have both a 50-50 ratio and a 60-40 ratio. And yet that runs through a pump station and into a storage tank and or a hot water heater. And this is where the particulars of the designs really come into play, and the sizing for the particular home is really important. We have both single coil and double coil water heaters. Some of them are still using, because these were all retrofits, so some of them still use the indirect fired water heaters that were in the homes, and some of them we replaced entirely with double coil tanks. You have a control unit over here, and then that runs basically into whatever application you're going to use, hot water and or space heating. So this can be used to directly preheat the water before it goes into a water boiler to use less fuel to burn to increase the BTU. Or you can also use that to run through your baseboard or hydronic or radiant floor heating to do space heating for the home. So generally, solar applications have been frowned upon a little bit in Alaska. But in our initial red screen modeling, again, I think done by Kat back there, suggested us a 50% solar fraction above the Arctic Circle where we are, which roughly pans out to maybe displacing 50% fossil fuels if the applications are done correctly. The big bonus that we see here is the off-the-shelf technology that can be readily transferred to other communities, off-the-grid applications or in villages. Alaska Battery Systems and Sioux City Energy Systems helped us with our contracting and did a lot of the installations with us. And they've done quite a few installations around the state, and if anybody wants some particulars from them, they are free for that. And again, we are north of the Arctic Circle, so we have some months where we don't have any sun. We estimated these would be viable about 9 months out of the year, and the data that I got this winter looks like it might be a few extra weeks on top of that. The main challenges have been that nobody's ever done this above the Arctic Circle, so we didn't really know if it was going to work. We can all sit around and think theoretically about how well things work, and then you try it out and go, oh, well, maybe this does or doesn't. So that was really the fun part. The main challenge operationally is maintaining the systems in cold weather, and practically the availability of a qualified plumber to help retrofit these homes. Which is sometimes more difficult than it ought to be. But here's a good example of maintaining something in cold weather. This is one of the Heliodyne systems. This is you see the pump station, which is actually insulated with closed-cell foam there. And behind it you can see the utility room of the house. Just to the right of this frame is the front door of the house. And we installed this and commissioned this about Thanksgiving, so towards the end of November. In the middle of December we had a severe Arctic storm. It got pretty cold, but the winds were gusting over 50 miles an hour, and there was enough wind that got through that door to actually freeze that pump station. So because we have a plumber extraordinaire who put in about 9,000 ball valves to be able to isolate the system, we're going to move this pump station inside that utility room. That's something we're doing right now, just to keep it a little bit warmer, and then we don't foresee any problems after that. The benefits, like I said, we estimate a 50% solar fraction, so we could reduce fossil fuel usage for these applications by about 50%. But conservatively speaking, we're estimating maybe a 30% reduction for domestic hot water use. And we really don't know what the reduction for overall fuel usage is going to be. That's part of our role with ASAP is collecting the fuel data over the several years, comparing it to the fuel data during the application of these projects, and then of course the heating degree days to get a nice round number to see what we're really dealing with, and of course the payback period on that. So this idea began back in 2008 when CETF was formed, as I mentioned before, and we selected, after we got the Denali grant, we started selecting homes, and we had a few criteria. The main one was that we wanted to focus in on helping people that needed it the most. So we decided that Elders Homes was a good application for this. We also needed them to be full-time residents of Kotzebue, and of course the home had to have a reasonable solar or southern aspect. The installations began in November, and it actually went rather quickly. Here's one of the more radical angles that we put on a roof. As a side note, these systems, the mounting systems are rated over 100-mile-an-hour wind capacity. This one, because of the way that it sits on that roof, we're actually going to add some extra guidelines to it. So as the project status is now, we installed 6 systems between November and December. We used 2 major manufacturers. Weisman, who you've already seen, who did the boiler for Sea Alaska, also does a variety of solar thermal applications. And we also used the Heliodyne system. So we did 3 of each to test which system was going to work better. Of each of those 3 systems, we did 1 evacuated tube and 2 flat plates. So overall of the 6 systems, we've got 2 evacuated tube systems and 4 flat plate systems. All of the Weisman systems are for domestic hot water only. They're designed particularly for that, and that's where you're going to see the greatest efficiency according to the manufacturer. The Heliodyne systems, we were able to tap in and do a combined domestic hot water and space heating application for the hydronic baseboards. All of the 6 systems were commissioned in December. And here's just some pictures of what they look like. On the left there, you're going to see Mary Omnick's house, and that's with the pump station cover removed, so you can see some of the plumbing in there. And then over there on your right, on Enoch Scheidt's house, you can see one of the low-angle collectors. And that's actually not snow sitting on there. That's a white covering that we put on, or that comes on it to decrease the amount of solar radiation that is collecting before we have completely installed the rest of the plumbing. So the big system, or the big questions for these systems, did these work above the Arctic Circle? And the short answer is yes. The long answer is quite long. Here's some initial data that I pulled. I was in Kotzebue last week, and I got this data off one of the systems at 1:55 p.m. If I had been there, if I didn't have to catch a plane at 2:55, I would have gotten more data that day. And what this shows right here are the temperatures. That red line that spikes up is the temperature of the collector outside the home. Now, I have to mention that this was, I think it was -30 or -35 wind chill that particular day, and the collector's temperature was over 70 degrees. We have seen collector temperatures over 120 degrees at the same ambient outside air temperatures. So this measures the flow rate and the temperature of the storage facility itself, the water tank, inside and outside of it, and how it's going to flow. And this is a BTU rating, and you can see here that the sun directly hit this thing at right about 1 o'clock, and it immediately started producing BTUs. This is not a lot of BTUs, but you have to realize that the sun is really, really low on the horizon right now in Kotzebue. And then it looks like it actually went behind a building, the sun, and the BTUs fell off dramatically. Now, we design these systems and we put them in places where they're not going to have a lot of outside obstruction from other buildings prior to these few weeks on each side when the sun is really low on the horizon. You will see some obstruction. And then this is last 30 days of fuel. You can see on the 3rd there of February, it's about when the sun came back to Kotzebue. And we got a few BTUs out of there. And then we had a winter storm on the 4th and the 5th. The 6th apparently was a sunny day, and we got 4,500 BTUs. And then we had another winter storm. And then we got the sun back, and we can see an increase in BTUs. Now, on the 12th, we got, it's about 4,000 BTUs, but that was only producing for about half an hour. So on a whole day, we expect to see quite a bit more BTUs than that. So how much fuel are we going to be saving? We don't know, is the short answer to that. We're going to collect 12 months of data, and we're working with ASEP to maybe extend that to 24 months of data. And we'll compare that to historical fuel usage for each home, and we can see what the offset is, and that, of course, is what is going to give us our simple payback, which is what everybody wants to know. Conservative estimate is 6 to 10 years payback for these systems, but of course that depends on the fuel prices. They are not static, as we all know. Okay.